Alright, to take the derivative of this, it's an implicit differentiation. If you look down here, what I did is, for this piece right here, I left a 3 out front, and I did a product rule of x squared and e to the y power. Derivative of x squared is 2x. Leave that, plus leave the first, and take the derivative of e to the y. I then took the derivative of this right here. There it is. Remember, when you take the derivative of e to any power, it's e to that power times the derivative of that power. And then over here, you have an ln 3x. The derivative of an ln is u prime over u. So the derivative of 3x is 3 over 3x. Now we have this ugliness. Now we got to get y prime by itself. So that's the work here. So it looks like what I did here is I simplified this and this, and then I distributed the 3 in. So when you distribute 3 in, you get 6. Distribute the 3 in. So this right here represents that right there. Then here, I simplified this because negative 4 times 2 is negative 8, and then brought the x in front. And here the 3's cancel. Alright, next step. Looks like what I did is I got the y prime to one side. So this is the only y prime. So it's kind of an easier one. I moved this and this over. Whoosh. And then now the last step is to get y prime by itself, so you divide this off, put it on the bottom. Now be aware, a lot of times you could have two separate y prime pieces, so then you'd have to yank out a GCF of y prime. So this does not actually give an example of where you pull a GCF of y prime out. So be aware, it's very likely you'll have to pull a GCF of y prime out. This one did not have that, so be very careful. Now the next piece, this one, take the derivative of this. Now you could take the derivative of this and do a chain rule with a quotient rule and all sorts of stuff. But hopefully you'll notice that you can rewrite this function as a square root as a half power and then put the half power in front. So you could have had a half power here and woo, throw it in front. Alright, so I forgot my parenthesis right there. Kind of interesting because there's one right there. Anyway, so the half power up front. Then, once you put the half power up front, do you see a division is a minus in log terms, so you can expand this as being ln secant, and then ln the denominator with a minus. So now we take the derivative of this, which is a little bit easier. I leave the 1/2 out front. Derivative of ln is u prime over u, so the derivative of this over this. So that's the derivative of this is that over that. You can see the secants cancel, leaving you tangent x. The derivative of this is 3x squared over itself. Just simply leave that. And then you could do simplification if you wanted, but that's a good enough answer for now. Alright, for this problem right here, we are doing a definite integral. Now you could do long division and take this divided by this, and that is another way of long dividing it and then making a new function. But what I'm going to do is I'm going to do u prime, u substitution, sorry. So I'm going to take my denominator and make that u, okay, and I took the derivative of that, which is just dx. And then you then resolve this for x. And what you'll notice is I then go, okay, I replace x with the u minus 3. See right there? I have 1 minus x. So I replace the u minus 3 with the x. My denominator is u, and my dx is now du. So I now have this. Now where did I get 4 and 3 from? Well, I took these two numbers and I plugged them into x plus 3. So I took the 1 plus 3 is 4. Take the 0 plus 3 is 3. Now my interval is in terms of u, so I don't have to go back to x ever again. Now I simplify the top. If you simplify this top, you get 4 minus u. Then if you divide both of these by u, you get 4 over u and 1, or minus 1. Okay, now we integrate this. This is just, okay, hopefully you know this, 1 over u, put the 4 out front kind of, so we stick the 4 out front, and 1 over u is just ln absolute value u. The integral of 1 is u. Now we have this notation. Now we just simply plug in 4, plug in 3. Plug in 4, plug in 3. You don't need the absolute values anymore because they're positive numbers, so they don't really need an absolute value. And you combine the pieces you're allowed to. So here's the answer. This one over here is an integral. So what I do is, you can see with this problem, I separated it into two separate integrals, and hopefully you can see this I wrote as a secant 2x. This one, all right. Now with this one, what I did, now some of you might think, oh, I could cancel this. Yeah, you could, and then you can make other problems, and that could be totally possible. You could have been a lot easier doing that. But let's stick with what we have. I made the u the bottom, secant squared, cosecant x is the denominator. I made that u. I took the derivative of that, which is right here, dx. All right, and then from there, I moved in. I got this, so I replaced this with u, so that is now u squared. The numerator is that, dx, and then the negative, I stick it out front. So now I changed this into a u integral, and then you got to realize if u squared's on the bottom, it's a negative 2 power. And then I took the integral of this, so I add 1 to that and divide by it. So I now have this. All right. I then plug u back in, which is cosecant. A negative negative is a positive, and then because it's negative power, I drop to the bottom. So there's where you get 1 over cosecant x. This piece is just all this. And lastly, 1 over cosecant is just sine. So all that. Now again, you could have probably gone a cosecant and cancel with here and work and simplify that and make this a really easy problem. It totally probably would have been easier. But I wanted to show you how to do it with all of this method. Now, right here, we have this one, okay, u has to be 2x, so when you make it du over 2 equals dx, because you had to divide the 2x over. So I now have secant u, and then dx is du, and move the 1/2 out front. The integral of secant u is this long thing, you just got to memorize it, plus c. Then I got to put u back in. All right. Now you see 2 plus c's. Well, you don't need 2 plus c's. You can group those together and just make another c because it's a constant and you haven't defined your constant yet. So let's combine those constants and just make it a different constant and put them all together. So there's your answer. Now you could put this 1/2 power back up and make that a square root if you desire. Both these are reasonable answers. Just be aware there's different ways of simplifying it down. Now, for this one, this integral, what I first noticed here is I first would say that I noticed my u has to be the power of e. So I have that's a u. When I take the derivative, I get this. I get 8x dx, and divide by 8 over. All right, now, hopefully you notice that this is the same as x dx. You have the 8 on the bottom. Okay, so you're going to x dx becomes du over 8. This is e to the u. Now this 5/3, they just threw it out front. Be aware of that. Some people get confused, but you can throw that 5/3 just straight out front. It's kind of nice. Then you can move the 8 with that, so you now have 5/24. And you have a real simple integral. The integral of e to the u is e to the u, yay, plus c. Don't forget that. And then we stick u back in. Boop, right there. All right. Now, if we want to find extremas and points of inflections, the first step you want to do is take the derivative. So this is u prime over u, and that's just 1. When I simplify this down, I keep simplifying, I go down to here. Now this is a good simplification at points, but you also want to maybe go down to this when you find your critical numbers. Okay, because right here, if you keep going, negative power drops to the bottom, multiply x times x over x, get a common denominator. Basically what it is, I set this equal to 0 and this equal to 0. So when I set that equal to 0, I solve, I get 2. There should be a 2 there. No, actually, there should be negative 2 right there. It's not written. There's an error. So I get 2. And here, if I set that equal to 0, I get 0. Now, so looking at my first derivative right here, these are my possible 2 and 0 are my 2 possible critical numbers. But when I plug 0 back into this, it's an error. You can't take a natural log of 0. So that's why it says not possible. That's not a reasonable answer. But if I do plug 2 in, I'm good to go. If I plug 2 into here and 2 into there, what you end up with is right down here. I plug 2 in and 2 in to the original function, and that gives you this answer. So when I plug in 2, I get this out. It does give me in value, so I can have this as a possible critical number. Then, okay, we'll come back to this. This is your critical number. Now I make my second derivative, so I probably took this and did the second derivative of this. This is probably the easiest to take a derivative of. That's why I went to this notation. So when you take the derivative of this, you get this in here in the blue, which simplifies to right here. You set your top and bottom equal to 0. Actually, you don't have to set -2 equal to 0 because that does nothing for you. So you set that equal to 0. You solve it, you get 0. And as we said earlier, 0 has an error. So the only place that could be a point of inflection doesn't exist, so there are no points of inflections. So the next step is, what am I doing here? Well, I'm checking what type of critical number extrema this is. So I plug in 2 to my second derivative. It's called the second derivative test. So here, plug it into this formula right here. Since it's negative, I know it's down, which means it's a min. It's a max, sorry. Because it's at the top, you know that this this extrema is a maximum because it's concave down at that point. Alright, this problem right here, I want to find the equation of the tangent line. So to find the equations of tangent lines, you need a coordinate. You have x, I need the coordinate and the slope at 1. So let's first find the coordinate. So let's plug in 1 to this function. That's all I'm doing here. By the way, the 4 goes out front. See why that 4 is there? I took the 4 and moved it out front. I put 1 for x. I put 1 for x. ln1 is 0. Anything with any log with a 1 right here is 0. And this becomes third power. And then you have 0 over e to the third is just 0. So there's my coordinate, 1, 0. So I'm partially there. Now I got to take the derivative of this. So this is kind of an ugly derivative. I think I first took the 4 and put it out front. That's why that 4 is there, just to make it easy on myself. And then I took the derivative of ln x, which is 1 over x, left the denominator, minus, leave the numerator. Remember the 4 got pulled out earlier, so just leaving it there. Leave that and take the derivative of this. Remember, when you take the derivative of this, you have to, it's that times the derivative of 3x. That's where the 3 came from. And then all divided by the denominator squared. That's pretty nasty. Now, I don't want to simplify that. All I'm going to do now is simply plug in 1. So I went and found all my x's and just took 1. So 1, 1, 1, 1, 1, 1, 1. Awesome here is ln1 is 0, so that's all 0. Awesome. When you plug in 1, you get e to the 6th. When you plug in 1 over here, you get e to the 3rd. So as you can see, if you keep reducing, you have 4 over e to the 3rd, because 3 minus 6 is -3, so it's at the bottom. So that's your slope. So here's when you plug in your slope, you plug in your coordinate, 1, 0, 1, 0. And when you simplify it, there you go. There's the weird-looking equation of the tangent line at x equals 1.